Okay, so now we are in that chapter in the website, and I really like it that you actually went to the miscellaneous chapter. I try to put a lot of interesting stuff there. So we're going to study a function, okay, and it's called the Möbius function, okay. Now, unlike functions like y equals to x squared or y equals to cosine 2x, this Möbius function is very intriguing and it's very interesting, okay. In 1831, okay, there's this guy called August Ferdinand Möbius, and he's the one that studied a function like this, which is why later it was named the Möbius function in honor of his name. Okay, 1831, and it was a function that really intrigued mathematicians because they really wanted to know, wow, how is this function useful? Okay, they did study it. Okay, obviously Möbius was the first one to study it, and then when a few other mathematicians came along, they discovered a lot of interesting aspects of the function, the Möbius function. Okay, so what is the Möbius function about? The Möbius function is about dealing and grouping positive integers, okay? Positive integers. So we got a Möbius function here, or I just write Möbius function, okay? And it's dealing with positive integers, all integers and all positive, including 1, okay? So yeah, we less 0 from the equation. Okay, so the Möbius function, and it's talking about, okay, if you like to use a illustration, okay, it's talking about 3 hats, okay? Like, yeah, a hat. Okay, you got one hat here, you got another hat here, and you got another hat here. Okay, I hope you can see them. Okay, and then we start labeling the hats, okay, as 0, hat minus 1, and hat plus 1. Okay, so we got these 3 hats, and we got a group of positive integers, okay, to be placed into these 3 hats. So when he was studying the function, this was how the grouping of the positive integers go. Okay, hat number 0, okay, we will put all the positive integers, okay, let's just say integers, we call it from now, all the integers that is a multiple of a square number into hat 0, okay? I say again, a multiple of a square number. Okay, so what does that mean? So, hat 0 goes as a multiple of a square number, okay, and then the numbers start going like that, 4, 8, 9, 12, 16, 18. Okay, why is that so? Okay, yeah, this one is 2 times 2. Okay, sorry, 4 is already 2 squared. Okay, so this is a square number. Okay, something like 9 is 3 squared. Okay, something like, say, 16. Okay, 16 is equals to 4 times 2 squared. So you see 16 is 4 times 2 squared. So as long as you can think of a positive integer, which is a multiple of a square number, it goes into hat 0. Okay, example, 18 would be 9 times 2. Okay, 9 is 3 squared. So you see, as long as you got that square number, it goes inside hat number 0. And if you got something like that, what you would write? You would write mu, okay, 18 is equals to 0. The Möbius function at the time, it was represented by the Greek letter mu, so we write it like that. This is the Möbius function, mu x, for example. Okay, so you see, we got a number 18, which is a positive integer, and the number 18 is a multiple of a square number. It's 2 times 3 squared, okay? So it belongs to the hat 0. So if we apply the Möbius function 18, okay, if we apply the Möbius function to 18, we get 0 because it belongs to hat 0. So that goes into hat 0, okay? Multiples of a square number, okay? Or another way you can call it, okay, it's called non-square free. Okay, the term comes in quite a lot later, so just get familiar with it. Non-square free. Because, why is it that? Because it is not square free. You can have a square inside, you see, it's non-square free. Okay, so multiples of a square number. So that goes to the hat 0. Now we got hat minus 1 and hat plus 1. Okay, before we start talking about them, we need to introduce the concept, okay, of the fundamental theorem of arithmetic. Okay, fundamental theorem of arithmetic. You know what it means? Do you know what the theorem goes? The theorem goes is that any positive integer can be factored into only a unique set of prime numbers. Okay, a unique set where the order is not important. Let me give you an example. Okay, 30. If I want to factor 30 into prime numbers, I will go 30 is equal to 2 times 3 times 5. Where these 3 numbers are prime numbers, okay? And there's no other way I can think of prime numbers that when I multiply them together gives me 30. Okay, now I can write 5 times 3 times 2. So like I said, less the order. The order is not important. So the fundamental theorem of arithmetic kicks in when we're dealing with head minus 1 and head plus 1. Okay, why do I say that? Because head minus 1 is positive integers that can be factored, okay, factored into an odd number of distinct primes, factored into an odd number of distinct primes. Okay? Remember, odd number and distinct. Okay, that one we need to pay attention about that. So head minus 1 is the integers that we put inside head minus 1 are those integers that can be factored into an odd number of distinct primes. Okay, and it goes as 2, 3, 5, 7, 11, 13, 17, 19, and 23. Noticing that early in the series, okay, they are all prime numbers. Okay, 2, 3, 5, 7, 11. Why is that so? Because 11 is equals to 11. It only factors into a prime number 11 because it itself is a prime number. But later when you go on into the series, okay, you see a number 30 inside there. That means 30 will go inside head minus 1. Why is that so? Because 30 is equals to 3 times 2 times 5, just like I've shown you. Distinct primes, and it's an odd number. There's 3 of them there. So 30 will go into head minus 1. So if we apply the Möbius function to 30, we get minus 1 like that, like so. Easy enough to understand? So head minus 1 are numbers that factor into an odd number of distinct primes go into head minus 1. And for head plus 1 is integers, okay, sorry, positive integers that factor into an even number of distinct primes. Seeing that it's even and it's distinct, okay? So, how does it look like? Well, it just looks like 1, 6, 10, 14, 15, 24, sorry, 21, 22, 26. 21, 22, 26. Okay, let's just take a look at it. 1, okay, for the sake of completion, Möbius decided to put 1 inside there. Okay, I know 1 can either go into here or here, but 1 just went into the head plus 1. You just dumped it inside there. Okay, 6 is equals to 3 times 2, even number. 10 is equals to 5 times 2. Okay, and 14 is equals to 7 times 2. All of them are distinct primes because we can factor them into prime numbers, but it's when there's an even number, okay, we put them into head plus 1. So that is just how the Möbius function goes. We got a bunch of positive integers and we apply the Möbius function to them. It gives us the result of 0, minus 1, plus 1, depending on which head the positive integer goes into. Okay, bear in mind that in a way I can just separate these two heads just when I look at it, because how do I do that? This one is with distinct primes. Okay, this is the main difference. It's distinct primes. This one it's not distinct. Okay, why do I say that? Because remember, this is a multiple of a square number. The square number would already make the positive integer, as it would already make the factors non-distinct. Okay, you just take for example like 18. 18 is equals to 3 squared times 2, okay? It's a multiple of the square number. This is the square number over here. Or shall I say 9 is the square number because 9 is equals to 3 squared. So 9 is a square number, okay? But the fact that 9 is a square number, it will mean that it's 3 times 3. So once you got 3 times 3, it is no longer distinct. For example, if you got 49, okay? Sorry, 49, is it? No, 40, yeah, 49, correct. If you got 49 times 2, okay, this number over here, which would be 98, I believe, 98, will go inside head 0 because it's 7 squared times 2, and the 7, you only got 7 times 7. So it's not distinct. Okay, so one way to look at it is that down here is distinct primes, down here it is square numbers, okay, which in itself make it non-distinct because you can, create two of them and multiply them together. That's what the square number is. Okay, so the Möbius function, and we will just talk a little bit more about it, looking into the individual heads and looking into the fundamental theorem of arithmetic, which I hope that you will enjoy. Okay, so there we go, brief introduction.